There are so many dark clouds in modern physics. Let's go back to classic physics of early 1900s and ask classic questions for elemental particles. Maybe it is time to revisit quantum mechanics and theory of general relativity. This is our new direction of physics.
Today we're going to continue our new direction of physics videos. So this is video number 10. So we're starting a new section, and this section we start talk about the scaling factor, and it's a dynamic variable. It's not just a factor, it's as a dynamic variables. And what we're trying to do over here in the next two videos, we're going to try to remove the infinities of the quantum field theory, and also to revisit quantum mechanics in a more physical way instead of just mathematical models. Okay. In the last video, we already derived the Einstein's energy, quantumized energy assumptions. Okay, so that's how energy relates to its frequencies. Okay, so how we did that? We just had a S times m over r c squared equals 1. That's our black hole boundary conditions of extreme black hole. It's rotating. Okay. So we can derive that. Okay. So we also showed that in the 1D box. Okay. If we have a particle, we see the quantum property of the particle movement in a box, and also the energy has to be quantized. Otherwise, they're going to get out of the box. Okay. So in this video, we're going to talk about why we need a scaling factor, okay? What it means to physics, okay? What is a scaling factor, okay? We're going to using this scaling factor to describe the virtual particle behavior, how it, what's the property look like, what's a virtual particle movement, or in basically we're trying to introduce this scaling factor and to describe the quantum mechanics in a more physics way instead of pure mathematics. So in the next video, we're going to show that how this scaling factor can be Planck-Type, can remove the infinities from quantum field theory. Okay, as we know that in the quantum gravity we have many terms of Feynman diagram like that. Okay, so it has different interactions. It can have many different terms, many interactions. Okay, so something like that. It became infinite number of infinities. After we introduce this scaling factor, all infinities will be gone. So what is scaling factor? Why we need it? Okay, so that's what we're going to talk about. And it's interesting that it's related to general relativity and quantum mechanics, this scaling factor. Okay, so when we see that quantum gravity has infinite number of infinities, people are thinking, oh, okay, we're going to renormalize, try to solve on the quantum mechanics way. Okay, our way, it's we modify that because the general relativity and quantum mechanics or quantum physics, okay, they are not compatible as our question when we ask. Okay, so what we try to do, we modify general relativity a little bit. Okay, we modify the quantum mechanics a little bit so that we're in the middle way. Instead of people say, okay, quantum mechanics, we need to redo something. Not many people talk about how to modify general relativity because general relativity, it's far away from being unified with other field theory. Okay, so let's see what we can do over here. Let's go back to our traditional questions. We asked the 6th question before Now we ask number 7, okay? Does vacuum has energy momentum? Okay. What do we see that vacuum doesn't have ether, okay? That's where Michelson-Morley experiment found that there is no ether, okay? Now our quantum theory put all energy back into vacuum. Okay, it's a vacuum and has energy momentum. What the current quantum theory, it's saying, okay, we have an uncertainty principle. Okay, when x goes to 0, energy momentum goes to infinity. It's a mathematics. Okay, it's a mathematics. But how physically possible? I mean, the current mainstream physics, it's say, okay, if we can explain the phenomena, we use the theory. But what is physics behind it? So now let's see that when the delta T goes to 0, energy also goes to 0. So in the Feynman diagram of electron travel in vacuum, okay, we have more 4D mass. It's created in a vacuum. Okay, so basically we're writing the four-dimensional energy and momentum. Okay, K0, K1, K2, K3. So what happened is in the Feynman diagram we have an electron travel freely. Okay, but in the perturbation theory, electron can emit in a virtual particle, and then that virtual particle can have energy and momentum. So what happened that it's k squared plus k minus k squared. Basically, the total. Let's say put it here. That's a total four-dimensional energy momentum. Okay. So by adding that together, so that's greater than p squared. P squared equals minus m squared in our description, okay? So we see that that's greater than mass. So that means if we do the d tau in 4 dimension like that, if we integrate our Lagrangian, we see that we have the d tau greater. So the idea what I have over here, I introduce a scale because this one greater than this one. Okay, so now I introduce a scaling factor, lambda. Okay, just a scale which allow them to be equal. What happened that now this lambda it's saying, okay, we have a mass. Okay, that's a free electron. We have a mass. Okay, we have a mass over here. So when it emitting a virtual particle, the 4D mass added together in the system is bigger. So how much bigger? Let's introduce a factor of lambda. Okay, that's a scaling factor. What it means? Okay, that means when you have a system has original mass, when you add a virtual particle, you increase the mass, the ratio of the mass difference, or the ratio between the emitting particle or no emitting particle, there is a factor. That's what we call scaling factor. Okay, that means how much extra mass you created. Okay, if lambda equal 1, that means no mass is created. If lambda is infinity, because if k squared goes to infinity, okay, you see that we have 2k squared over here. It's much, much bigger than our initial mass. That means lambda goes to very big. Okay, so if we introduce a scale into physics, we will see that what happened is all different physics variables, they have different weight. Some of them lambda squared, some of them minus lambda, minus 1, some of them lambda 3. They're all different physics variables. Physics variables has different scale of lambda. That means if we rescale this especially if we're adding more perturbation, we're adding more scale, and the sad thing is, and lambda is different for all the perturbation terms. So that means we're randomly adding something, and also there are different square, lambda cubic, lambda minus, all this in our physics. But why all physicists didn't realize that? Okay, because in the quantum mechanics, in the phenomenology, mathematics describe everything. Just people didn't realize, okay, we're introducing more mass over here. Why physicists, the current mainstream physics, they don't realize that because they said, okay, we borrowed a very short time, okay? So basically, we short time violating the law. We're fine. But then if you violate the law, you will have a consequence, okay? So, I mean, I was talking to a friend of mine, okay, can I borrow some money from you? He said he needs interest, okay? Now we're borrowing something from the vacuum. It's no cost and no limit, whatever we want, okay? We can emit in K small, K big, all Ks, whatever, okay? So this doesn't make physics sense. But I think there are also another reason why people are scared of introducing these, because the physics law doesn't allow us to introduce another factor or another variable to the physics equations. We will see that. How can we do this? If we allow only lambda, it's energy momentum dependent, not coordinate, okay? Not coordinate. Okay, we will see in the next video, if lambda is only depends on energy momentum, not coordinate, all physics equation doesn't change, okay? So the physics core equations and the physics variables remained. So that means if we bring something new to physics, we need to think about the scale, okay? So that means all perturbation, we have to think about this. So that's why we need to introduce scale. But now we go back to Einstein's general relativity to see what issues Einstein's field equations has. Okay, this is a very brave claims, okay? You're talking about issues with Einstein's general relativity. This has to be very brave, okay, to say that. But what I think the concept of general relativity, it's perfect. General covariance, general the flat space locally, things like that, all are very good. But Einstein's field equation has some issues. That's what I'm trying to claim. Okay, so Lagrangian for particle moving in a tensor field, metric tensor field, is like that. So we have the equation that's called the geodesic equations. Okay. Geodesic equations. Okay, what's the issue with Einstein's field equation? We already know that Einstein's field variable, it's gamma like that. It's not a tensor. All our other physics are tensor, okay, except general relativity. Okay, it's not a tensor. But in the end, the field R mu nu, it's tensor, yes. Einstein's final equation is a tensor. But the variables equivalent to A mu, okay, partial A mu. So something that's equivalent to the partial A mu, partial xv minus partial AV, partial x mu. That's in the Maxwell equation, okay. This is tensor A mu, it's a vector, okay. So it's like one tensor, okay. So Maxwell equation is vector and tensor. But Einstein's field variable equivalent to this, it's not a tensor, okay? We know that 100 years ago when Einstein first proposed that. That's not a real issue I'm trying to claim over here. But in Einstein's field equation, he has a term like that. Also, it's a field variable, which is a derivative of scalar. Okay? But it doesn't have the self-interacting term of the scalar. That's what I'm trying to claim. Okay? Yes, Einstein's field equation means a self-interacting scalar term. People say, hey, Q, you just introduced the scalar field, okay, scalar self-interacting. When Einstein proposed that, he has curvature, everything is very natural, okay. So because I introduced the self-interacting field theory, we see that they're missing that. I mean, Planck-Type, okay, and they proposed a scalar theory to add into Einstein's field equation, but the test results in the end didn't support the theory. Okay, we do it differently. We are not just add extra term. We put this term, we separate that term into, separate it out. We add another extra term of self-interacting, okay? So if we separate Einstein's field variables like that, okay, the first term on the right-hand side, this term, it's a tensor, okay? The second one, it's a Minkowski space of affine connections. It's not a tensor. Basically, I'm separating Einstein's field variable into a tensor plus an affine connection. But the affine connection of this term, it's a flat spacetime, Minkowski spacetime. We don't mind that, okay? Let's study that, the difference tensor, okay? So that means I'm going to rewrite Einstein's field equation into that. Hey, Q, you're talking about scaling factor. Why you're jumping into general relativity? General relativity has a scalar term where I'm trying to introduce, but that's interesting because Einstein's scalar term is like that, okay? It's a Jacobian, okay? It's a Jacobian, that means it's a scaling factor, okay? It's from the Minkowski space to the metric space with matter. There is a Jacobian, okay? So this Jacobian, it's a scaling factor, okay? It's a scaling factor, okay? So that means we see that Einstein's general relativity, if we introduce a scalar field, I mean, Einstein already have that, but only the divergent term, not the self-interaction term. If we introduce that, okay, so we have a scaling factor being introduced. That's a Jacobian, okay? So that means Einstein's field equation, we're trying to modify that. We need to introduce a self-interacting scaling factor, okay? If we repair that, why don't we put it into quantum mechanics, okay? So see that what we have over here, by adding extra term of self-interacting into Einstein equation, does not cause me troubles on general relativity, because general relativity has all these classic tests, okay? People has tested. Now, if you add extra term, just like Planck also add extra term, but then the experiment to prove that that extra term is not good, okay? We add an extra term, hey, so are we going to be in trouble? Also, the good news is that because all the general relativity class test is based on the Schwarzschild solution, and this term is equal 0, okay? So we are introducing, we add a self-interacting term, this term is 0. So in the spherical symmetric, we're not adding extra term because it's 0, okay? Under the asymmetric system, we have a trouble. In the symmetric term, that's Schwarzschild solutions, yes. If people say, hey, we test the general relativity, yes, you test my theory also, yeah, because this term equals to 0. Okay, so this self-interacting term, why I'm bringing this? Because in one of the previous video, we already showed that, okay, the quantum mechanics potentials, quantum potentials, is similar to the self-interacting field theory. If we want to bring the general relativity in, we have to have this term, because to match with quantum mechanics. Quantum mechanics have a self-interacting term, okay, like that. So that means if we add a self-interacting term, scalar self-interacting term into general relativity, we have a term match quantum mechanics, okay? So this is why we are proposing this, okay? So also the scalar term and tensor term, they have opposite sign, okay? One cancel with the other one, okay? The self-interacting theory will limit the black hole. You cannot keep going, yeah, because this self-interacting term will limit the black hole. You can't go infinities, okay? So yes, I'm bringing in the scalar term, a self-interacting term, into Einstein's field equation. Let's call that modified general relativity, okay? So that means the good thing is we don't need to worry about the test, okay? So now we need to see the difference, then we test that, okay? Any classic test, you can go ahead. We're in this Feynman diagram I already talked about, okay? In special relativity, okay, in the Einstein special relativity, it's like that. No mass is borrowed. Now we introduce a variable to see the effects, okay? We see that it's in general relativity. Why I'm going back to this, okay? Because now if we see that we can only borrow K, maximum K, its mass, m. That means if you borrow some virtual field from your parent electron, the maximum you can borrow is mass m. So remember the mass, the self-interacting term in the Feynman diagram, you have a mass correction term. Because if this equals m, this goes to 0, okay? That's a beauty. One of the infinities in the quantum field theory, it's gone, okay? This one is gone without introducing anything. Because the most amount of energy momentum you can borrow from a parent particle, or you can only borrow the maximum they have. Or you can borrow money from a bank where the most money they have, all the money they have. The scaling factor we're introducing a cutoff function. Okay, that means we limited how much you can borrow. Okay, so that's the beauty by introducing the scaling factor. Okay, so let's see. Okay, I published a paper. I put it on ResearchGate a few years ago, or maybe a year ago. So that based on this Sakura quantum mechanics, we can rederive a lot of things where we see that that's the Sakura's way of the renormalization. So now if this equals mass, this term equals 0. So, okay, so we have scale factors in the paper. If you need to see the detail, we're going to put it into the YouTube channel. You can find this paper, okay? So all this, how the integral happened, the electron self-energy, how it introduced, what's the scale factor look like, okay? So in Dirac equation, when he bring into that the phi equals lambda phi, okay, or phi equals e to the alpha something, okay. So there is another symmetry for Dirac equation that's lambda is only energy momentum, not a function of coordinate. That means this equals 0, okay, because the lambda it's only depends on energy momentum, the energy scale, not the coordinate. That means a system has more energy created, you need to change that. It's not the coordinate, okay, it has nothing to do with coordinate, okay. So this is a paper about, okay, so now let's see what the scaling factor, okay. let's assume, we have to assume something, okay? We assume mass scale equal 0, okay? Mass scale, the scaling factor equals lambda 0 equals 1, okay? The charge, let's don't do anything with charge and the mass, because that's where we would like to start, okay? So, but then we have the energy energy momentum P mu equals m dx mu d tau, okay? We have a d tau over here, so because my scale is proportional to tau, that's why energy momentum has -1, okay? So for this electromagnetism and gravitation, you can redo all these, okay? Find the scalar weight, okay? I mean, this is lambda, that means P mu has lambda -1, okay? The scale. The curvature, scalar curvature -2, okay? The current, okay? It's, the current is -3, current density is -3. So you can derive all these, okay? Based on these assumptions. That means all physics variables has a scaling factor. This factor depends on the energy momentum. That means when you create a new space-time or you create more mass to the system, all this variable needs to be adjusted. Okay, the quantum field theory, I already derived everything, okay, in here. So what's interesting in that's why I said the electromagnetism, if we want the function of phi to be invariant under a scale, there is also another possibility, but that's Rander's metric, okay? Okay, so that means d tau equals square root of g alpha beta x dot alpha x dot beta plus, okay, so something proportional to E, I think it's E over m or a mu dx mu. That's the Randall's metric, okay? So Einstein was bothered by this. Say, hey, why it's square root of this? Okay, because this is Einstein's, okay? When the Randall's metric was first proposed, Einstein said, my God, it's what's going on here, okay? So we will come back to this, okay? So this means like electromagnetism has a symmetry like this, and also we can assume lambda equals only energy momentum, okay? Energy momentum or P, okay? Sorry, the only, not coordinate. X, no, not X, okay? So that's another symmetry. But once we have a scaling factor, we're introducing a cutting off function, okay? If we bring the Planck term, okay? But last time Planck's term is related to the frequency, okay? The frequency V, okay? And temperature, okay? That's for the black body radiation. Now we are related to mass and the K, okay? So mass is like a temperature. That's how much you can borrow from the parent, okay? The temperature is like T, okay? V is what the frequency you are emitting, the photons, okay? So now we have a mass, okay? That's like T. We have a K, that's how much it's emitting. But what's interesting, this scaling factor we're introducing, it's for virtual particles to emitting out and take it back. That's our 1D trapping of the field. You go out and then come back, okay? So by doing that, the beauty of the Planck term, when K goes to infinity, okay, the integration became finite. When K goes to 0, the integration also goes to finite. So there's no infinity anymore. either k it's positive or k squared or kn, n greater than 0 or n less than 0. Okay, n equals 0, that's constant. Okay, so both are fine. That's the beauty of the Planck term. Okay, so once we have the Planck term introduced, all perturbation theory, now you can do calculations. Okay, but the current mainstream physics is trying to find way to remove infinities. I think it's what we need to study. We need to study the lambda. Okay, basically we're introducing a new variable for physics to study. So basically what we need is we need to study the electron, how it emits virtual particles. Okay, how the field been emitted, how it been taken back. But that's general relativity because our field emitted and taken back. Okay, so that's the self-interacting field theory. We're trying to, I think we need to study that instead of finding ways to remove infinities. In summary, this section, this video, we talk about from the geodesic equation, we see that we need the scaling factor to Einstein's field equations. We need to bring the general relativity. That way we bring general relativity closer to quantum mechanics because we have the self-interacting term. Okay, so even though it's 1/2 over here, the full theory will be 3/4. Okay, we can introduce the cutoff function to quantum mechanics. Now all infinities are gone. Okay, so in the next video, we're going to talk about how to remove infinities. By that, we're going to talk about the quantum physics space-time. Okay, we're going to continuation on the scaling factor of energy momentum and quantum entanglement of 1D field exchange. Okay, thank you.